Well, it's great to be back here. Hey, Duncan's right. I represented the Winklevoss twins and Vivian Arendra in the Facebook case, and started in 2004, believe it or not. And that was made into a movie, and in the firm there was joking about who would play me in the movie. As it turns out, the lawyers in the movie aren't real characters. Everybody else in the movie is real, but the lawyers aren't. They kind of use the lawyers as a vehicle to move the movie along. But I was voting for George Clooney. But it never happened that way. Anyway, about 2 years ago, I was here and I gave a speech about 3D printing and intellectual property issues. And since that time, and since I gave that speech, which was, I believe, in March or so of 2013, I've given 52 speeches on 3D printing all around the world, and I've turned down another 37. So it's a really, really hot topic. And usually what I talk about is 3D printing and its relationship with intellectual property law, how it can affect IP and how IP can affect it. But, and that's kind of what I talked about in Melbourne at the meeting last week. But what I'm going to do today, and also what I'm going to do in Perth on Wednesday, is I'm going to talk about the technology itself and what's happening, who's trying to get into the space, and also what's happening in Australia. And I think it's really important for people who are in IP law to understand this technology, because it potentially cuts across all technology, all companies, all of your practice, and all types of intellectual property law. But yet most people think that 3D printers are these little machines that print out Yoda heads. And that's the common thing that you see. But that's only, and that is part of 3D printing, but that is one very tiny part of it. And that's also only one type of tech. I shouldn't say a tiny part of it. That type of machine is the most common type of machine. But that's only one type of 3D printing process, and those are also consumer-grade machines. And the really exciting stuff, I think, is what's happening in industrial machines. So what I'm going to talk about today is the technology itself, so you know more about it. And so when clients come to you with an issue, or maybe even when you are dealing with startups, or you're dealing with companies that are interested in getting into this area, you can talk about the technology intelligently. And now, first I want to talk about what I call the name game. Now the name game is what to call this. A lot of people call it 3D printing. I call it 3D printing, but some people call it AM, or additive manufacturing. And there's every conference I go to, and I go to a lot of conferences, there's always this either a debate about what to call it, or some people will call it AM, or additive manufacturing, or they'll call it additive, and other people will call it 3D printing, and you can always feel this tension about what to call it. I call it 3D printing because I think that term is sexier. I think it helps to drive the adoption of the technology. And if I ask you, what would you rather see, my brand new 3D printer or my brand new additive manufacturing machine, which one would you rather see? Right? So, and when you talk to people on the board level, people on boards, they're interested in 3D printing. People on the operational level might talk about AM, or additive manufacturing. The other thing is that additive manufacturing is sometimes used as kind of the opposite, to refer to the opposite of subtractive manufacturing, meaning the old way of doing things. Subtractive way was to take a billet of the material and drill it or mill it, and so they say additive is new, and additive doesn't subtract. You start with nothing and you add material until you have something. I don't really think that's a good, accurate description, additive versus subtractive, because there are some processes that are both old and additive. And for example, weaving, casting, and injection molding are all additive processes. So I don't like to refer to the process as additive versus subtractive. Instead, what I like to talk about is additive or 3D printing versus traditional manufacturing methods. Now, as you'll see as I go through this and I talk about this, 3D printing or additive manufacturing, they're really umbrella terms. It's really an umbrella term for certain types of technology. Oh, Duncan, I'll try to stay in one place. Because I tend to wander around, so people who are trying to film often have trouble with that. Anyway, these are umbrella terms for what's really an alphabet soup of acronyms. If you get into this area at all, you'll start to hear about SLS, or you'll hear about DMLS, or you'll hear about FDM. And some of these things are generic terms. FDM is fused deposition modeling, and SLS is selective laser sintering. And some of those are either generic terms, or they're kind of quasi-generic terms, or quasi-trade names that companies are using, and they're used kind of, not inconsistently, but in kind of a confusing alphabet soup manner. So what I use instead is the names for the industrial 3D printing processes that have been adopted as a standard by the international ASTM. So what you see on the screen now are the 7 standard terminology types of 3D printing processes. I'm going to talk about each one of them. Binder jetting, directed energy deposition, material extrusion, material jetting, powder bed fusion, sheet lamination, and vat photopolymerization. These are the official terms. Very few people in the industry use these terms, and often are not used consistently. I and a few others in the industry are trying to kind of push the adoption of this terminology because it makes it so much easier to understand. And you'll see that as I go through. I hope you'll see that as I go through this presentation. Now, one thing I wanted to say about where 3D printing is today, which kind of is to kind of set the record straight on this belief that, you know, 3D printers are these things that make Yoda heads, is that the price range for an industrial 3D printer, and that's an example of one of them, that's a constant laser machine there that you see, and it has a crane, because when you take the piece out of the bed that's made in this machine, and or if you're filling up the bed with powder, it weighs 3,000 pounds. So you've got to have a crane to move the pieces in and out after they've been made. And the price range for an industrial 3D printer is anywhere from $5,000 to $2 million. And the price range for consumer-grade printers is considered to be anything below $5,000. So the industrial machines, basically, they go up to $2 million. The average selling price, as of 2014, is $87,000 US. That's actually down from $90,000 the year before. And there are about 80,000 industrial-grade machines installed around the world. Okay, so there's a lot of them out there, and there are more and more all the time. The number of the prior year, I believe, was 67,000 machines. So there was an additional 13,000 industrial machines installed in 2014. However, I kind of view the state of 3D printing technology as where the steam engine was in 1765, right? Now there was a steam engine. There were steam engines long before 1765, but it was in 1765 that Watt created the first practical steam engine, and it was a great invention for its time. It was pretty primitive compared to where the engine is today. And I kind of analogize 3D printers to where the steam engine was in 1765. Now it's not going to take 240 years to get the technology of 3D printers up to where the engine is today, because things are happening at an exponential rate now. But I think the technology is great, but it has a long way to go. Now, the first type of 3D printing technology that was on that list, and I go through them alphabetically, is binder jetting. Now, binder jetting is kind of like 2D paper printers, where you're using these inkjet heads, and what you're jetting out of those heads is a binder, and you're jetting it into a bed of powder. And that powder could be a polymer, or it could be metal, or it could be ceramic, it could be glass. So you have a bed of material, and you're jetting the binder onto that material layer by layer by layer, and you're building up a product or a part layer by layer by layer by gluing it together, essentially. And after the parts come out of the machine, they all need some kind of post-processing. Another kind of a myth is that when a part comes out of a 3D printer, it's perfect, it's beautiful, you can use it right away, and that's not true. Every type of technology that you'll see today has some type of a post-processing involved. And with binder jetting, there's curing involved, there's heat treating, and also infiltration. I'll talk about that in a moment. But one of the great things about this process is that you can make full-color parts. And here's some examples. 3D Systems, which is one of the top players in the industry, that's it's what I call an organic company. It's grown up purely in the 3D printing industry. It's not like an outside company that manufactured products for years and then decides to get into 3D printing like HP. And I'll talk about HP as I go on. 3D printing is homegrown within the 3D printing industry. 3D Systems, I'm sorry, is homegrown in the 3D printing industry. They have machines called PolyJet. They're US-based, and they have machines that have different build volumes. Some are small and some are large, so you can build big things. They build their products with acrylate powder, and that's what's in the bed, acrylate powder. And then after the product is made, it's infiltrated with cyanacrylate. Does anybody know what that is? It's a crazy glue. Yeah, it's crazy glue. That's what we call it in the U.S., crazy glue. And these machines run from about $16,000 to $114,000. Prices might be slightly varied this year. These are 2013 prices. Now, that's a plastics machine. Another plastics machine is this machine that's made in Germany by a company called Aerosol Jetting. And the beauty of the Aerosol Jet machine is it's continuous build. So you start building in one end and the parts coming out the other end, and they used it to print this James Bond's Aston Martin DB5. They made 3 of these for the movie Skyfall. And this machine uses polymers or sand, and it cures at room temperature, which is great because the products don't need heat treatment, they don't warp. And you can see these machines are fairly expensive, $150,000 to almost $2 million. There's another company in Taiwan called Microjet Technology that has a full color binder jet machine. Now there's also metals in this area. It's not just plastic parts. And there's a company outside of Pittsburgh in the United States called X1. They also have offices in Germany. And they have a fairly large build volume. And as you can see, they use all different types of powders: bronze, Inconel, iron, stainless steel, and also tungsten, glass, and sand. And when these parts come out of those machines, they are infiltrated with bronze. And first the binder is burnt out. They're heat treated to burn out the binder. And then they're infiltrated with bronze to make the part 98% dense. And these machines, again, they're expensive, $150,000 roughly to about $1.5 million. And as you can see, they're big machines. Now, this type of technology, this binder jetting technology, this is what was originally called 3D printing. Eventually, the term 3D printing became this umbrella term to talk about all of these different processes. But this is the original quote-unquote 3D printing process, which was developed by MIT, and it was licensed to X1. It was also licensed to a company called Z-Corp. Z-Corp was later acquired by 3D Systems, and then they sub-licensed it to VoxelJet. So what you can see from this is that all of the companies that are operating in this space, or almost all of them, they're licensed by each other, or they're cross-licensed in some way. And that's a good thing in the sense that it has now enabled the technology to move forward without litigation. And because I think litigation would interfere with the adoption of this technology. So it's good that there hasn't been much litigation. But the bad thing, I think, is that because of the cross-licensing, there hasn't been a whole lot of incentive to innovate beyond whatever technological path they happen to be on. So they're going down these paths. You have incremental improvements. Machines are getting better and better, but nothing amazing, nothing new and amazing is coming. And this technology has been around for 30 years. Well, this one hasn't, but the 3D printing technology in general has been around for about 30 years. Now, the second type of process is directed energy deposition, and it's also known as blown powder, and it's also known as laser cladding. And there are different manufacturers that do different types of processes. With binder jetting, each manufacturer is basically doing the same thing. They're spraying a binder onto a powder bed, and they're building up a part layer by layer. With directed energy deposition, you have different manufacturers, and they're doing basically different things. And here, the machine, the parts that come out of the machines, they have to be finished. They need some finishing done to them, surface finishing. But the parts are very strong, so you can make structural parts, and it's good for repairing parts. And these machines range from about $350,000 to $1.5 million. Now, one of the companies that's in this space is a company called Optimec. It's in the United States, and it's in Albuquerque, New Mexico. And they have their own process that they call laser engineered net shaping, or LENS, L-E-N-S. So this is one of this is their term. It hasn't become generic. This is their term, but it is one of these alphabet soup acronyms that you hear. But you might hear laser engineered net shaping, you might hear LENS or LENS, but it's really a type of directed energy deposition. And here what happens is you have these inkjet heads that spray powder through the inkjet head to the focus of a laser beam. So you have a laser beam and the inkjet heads together. They're spraying powder to the focus of a laser beam and depositing that. So you're depositing kind of a fused material with the use of that energy at the same time. And you can build it up in any shape, on any substrate, any shaped substrate. And this process was actually used by RMIT University here in Australia to repair turbine blades for a company that formerly bought hundreds of turbine blades every few years, and they'd spend hundreds of thousands of dollars to do that. And they started using the lens process to repair those blades or to replace those blades. So this is great for the company that needs the blades, as you can see. Great. Terrible for the company that sells the blades. You can see how disruptive this technology can be. Totally changing the way the products are made, sold, distributed, and used. And also totally changing who's a manufacturer and who's a customer. The customer becomes a manufacturer. And these use fairly powerful lasers. And the lens process also has the ability to make materials on the fly, alloys on the fly. So when you're shooting that powder to the focus of the laser beam, you can mix the powders as you go, and create alloys on the fly. And as I was saying, you can deposit on any shape of a substrate. So it can be round, it could be, you can deposit on the outside of a sphere, and the machine has a multi-head axis that basically a five-axis deposit heads, laser heads, so that you can go around and deposit on any type of a shaped substrate. Now another machine, or another company that does this is in the United States called Skyaki, and they use, instead of a laser beam, they use an electron beam, and then instead of using powder, they use wire feedstock. And NASA wants to use this process on the International Space Station because of the wire is the feedstock, so you don't have to worry about gravity. With powder, you need to worry about gravity. So, and you see a wide variety of materials: titanium, stainless steel, Inconel, copper, nickel alloys, and it's a very fast process, but you get very rough surface parts out of this. But they're very big machines. You can see this. You can make really big things with this machine. You can lay down a lot of wire very, very fast. Build up parts very fast, but they're very rough. There's some other companies in this space, some who sell products and some who don't. So NASA doesn't sell a product. Honeywell has something they call ion fusion formation. They don't sell a machine either. They just use the process in-house. There are some hybrid machines. There's a company called DMG Moriseki, which is a joint venture between DMG in Germany and Moriseki in Japan. And their process, their alphabet soup process is called, they call it laser deposition welding. Laser deposition welding, but that's their term, that's their trade name for it, but it's really directed energy deposition. And they combine their deposition head with a 5-axis mill, and they mill the parts as they go along. And the parts that come out of this machine are just beautiful. This is a rough part. This is what it looks like when the material is being deposited with the directed energy deposition process, and then this is what they look like after they've been milled as they go along. And they're just beautiful parts that come out of this machine. Yamazaki Mazak just came out with a machine that's very similar. It combines a milling machine with a directed energy deposition head. And now, material extrusion is the next type of process on the list, and this is also known by some alphabet soup names: fused deposition modeling, FDM. That's what you hear most commonly, FDM. And that's what people use mostly in industry. Also, you'll hear fused filament fabrication, FFF. But again, it's all type of material extrusion. And here what's happening is the thermoplastic is being extruded out of the heated extruder head and onto a print bed. The print bed may be heated or not heated, depending on what kind of material you're using. If you're using PLA, the print bed is not heated. If you're using ABS, it is. And here in this process, you may also be extruding a second material through a second print head to have support. So if you're building anything that has any kind of an overhang to it, you have to build supports under it so that those overhangs don't droop. And then after the part is made, you remove that support material. It's often, most of it's soluble support material, so it's removed with either water or a solvent. And again, these parts need to be surface finished as well when they come out. And you know what these look like. This is what they look like, the Yoda heads that come out of the consumer grade machines. On the industrial level, there's a much finer resolution, but still you can see the layers, and you need to do surface finishing. So these types of machines are great for prototyping and for certain types of end-use parts if they're just simple replacement parts like a handle or something like that. And there are all different types of thermoplastics that are used here. Some of them are proprietary and some aren't. And this is the most used 3D printing process in the world for two reasons. One is because of all consumer grade machines that are out there. And the other is because of the high-end machines that are out there are used for prototyping. And up until a few years ago, and this technology has also been around since the 1990s. So up until a few years ago, all of the work that was done in this area was called rapid prototyping or rapid digital manufacturing. And it's only been very recently that everyone started calling it 3D printing or additive manufacturing. And but this is the type of machine that's been used for rapid prototyping for many, many years. Now, even though this presentation is about the industrial side of 3D printing, I just wanted to give you a flavor of the consumer side. These are consumer machines, and in 2009, the basic patents in this space started to expire. Stratasys had the first patents. 2009, they started to expire, and even slightly before that, some startups started to enter this space, especially open source. And so there's at least 300 companies out there that are making consumer grade machines, at least 300. They're almost uncountable because many of them are startups. They're doing Kickstarter campaigns or Indiegogo campaigns, and nobody knows really how many they're selling or even how many there are. And they're all over the world. They're everywhere. And these machines go for $500 up to $5,000. And I've given you a couple of examples. This one here is called the Rova 3D. It can print in 5 different materials, 5 different colors at the same time. That one's I think a little less than $5,000. These are the 3D printing, 3D systems machines, and they have machines that run from about $1,200 up in the consumer space. And then here we have MakerBot. This is a well-known brand, now owned by Stratasys. This started out as an open source project when they were acquired by Stratasys, or maybe shortly before that. They closed their system, filed a bunch of patent applications, really annoyed everybody in the industry who said, well, there's plenty of prior art for this out there, but you know, that just created a huge burden for the open source community to challenge these patents. But they have a range of machines that run from about, I think around $1,800, $1,900 up in the consumer space. This machine here is called Markforged 3D, Markforged, I'm sorry, and it extrudes both thermoplastic and carbon fiber filaments, so you can reinforce whatever it is that you're making with carbon fiber. And this one sells for about $5,000. And then this one here is very interesting. This is the Luminar Tribot, and that one sells for about $5,000, but it combines material extrusion, CNC mill, and injection molding into one machine, consumer grade machine, which is pretty exciting. So that's taking a look at the consumer side of material extrusion. Now on the industrial side, we have Stratasys, which is, I would say, the top player in this part of the industry. It was a US company from Minnesota that merged with an Israeli company called Objet. And Objet is really kind of the tail wagging the dog, and therefore this is now considered to be an Israeli company. So at one time, the big chunk of the material extrusion market was US. After that merger, now the big chunk of the material extrusion market is Israel. In these machines, and you can see they have a whole range of machines of different sizes. They 3D printed this prototype of an engine, and they used this material called OurCam, which has great fire and smoke resistance. And the material here comes in spools, and it's fed into the machine, and they also support materials, like I said before, if you're trying to build with an overhang. And the machines run from about $10,000 up to about $500,000. Now there's a company in Germany called Arbor, which makes what they call a freeformer, and here they have a stationary nozzle, and then a 3 or 5 axis bed. And so the bed moves, the nozzle stays still, and it deposits droplets of material at very high speed. So it's kind of spraying out droplets of material. So it's not being extruded through a nozzle, but it's being shot out of a nozzle at high speed. And it's similar to a process called ballistic particle manufacturing, which I'll get to in a couple of minutes. But what's significant about this machine is it doesn't use rolls of filament, spools of filament. Instead, it uses injection molding pellets, thermoplastic pellets that are used in injection molding machines. So the cost of the materials is much, much lower to use this machine. But I think that the parts that are built up with this machine are actually fairly primitive and rough. So it's hard to say what kind of a market they're going to have. Now, material jetting, remember at the beginning I mentioned binder jetting, where you're spraying glue basically onto a bed of powder, building up the part layer by layer. Well, material jetting is actually jetting the material itself through a print head like you would have on a 2D printer. And there are different types of material jetting processes. Just like with that directed energy deposition, where there are actually different types of processes, there are different types of processes that fall under the heading of material jetting. And one of those is aerosol jet. I'll talk about that. The other one is ballistic particle manufacturing, and the third is PolyJet. Now, Optimec, which I mentioned earlier because they have a directed energy deposition process, a US company, they also have an aerosol jet process. And this, kind of the alphabet soup that is used here is direct write, or DW. So companies that do this type of 3D printing, they're often called direct write companies. And the method here is that you have heads like inkjet heads you'd have in a 2D printer, and they're spraying out the material itself, onto a print bed. And it's really what it's sometimes referred to as 2.5D printing, because this process is used, and I'm not talking about material jetting, but I'm talking about this type of material jetting called aerosol jet. This process is used for often for repairing things or for printing circuitry. And so basically you have some thickness to what you're printing, so it's not purely 2D, but it's also not building up a 3D product, so it's often called 2.5D. You can print onto any substrate, any shape. It's great for when you need extreme accuracy, and it's great for circuitry. And the post-processing here is heat or chemical treatments. Now, there's some other direct write companies out there. Strangely, 3 of them are in Israel. One's called Camtech. There's also one called XJet and Nanodimension. There is a company called Argentum, which I thought until very recently was a US company, but this is actually a consumer-grade electronics 3D printer maker that is an Australian company that has just moved to the US. And the reason I know that is, Bob, you sent me an article just a few days ago saying that this company was moving from Australia to the US, and you said it's a common problem, right? Well, until I got that article, I thought this company was a US company. But what they've created is a consumer-grade PCB printer, printed circuit board printer, that sells for about $1,400. They had it on a Kickstarter campaign, and the machine is called an Argentum. I think the company is called Descartes. And they started out here, and they're apparently moving to the US. They have not delivered any of their printers yet, though. The Kickstarter campaign was almost 2 years ago. So,
I think they're here in Brisbane, or they were here.
They were in Brisbane. Okay. Okay. So they were in Brisbane, and now they're moving to the US. So, but again, I don't think they haven't delivered my printer. I know that. So I don't think they've delivered any printers yet. Now, ballistic particle manufacturing (BPM) is a type of material jetting process that, as far as I know, no one is doing it now. But there was a company called BPM in South Carolina in the United States that was doing this process. And here you had an inkjet-like nozzle that's firing thermoplastic at really, really high speed. And just from the firing of the material, you were building up a part. And they were doing this with plastics. Now I'll tell you why that's important in a moment. And this was good for prototyping, but you got kind of rough parts out of it. And like I said, there was a company called BPM in South Carolina in the US. It's out of business. There was also a company called Incremental Fabrication Technologies that was doing this with metal. And I believe they're extinct. I can't find any evidence that they still exist. But what's significant about this, I think, is that it's very similar, at least what Incremental Fabrication Technologies was doing. It's similar to what CSIRO is doing in its cold spray process. And CSIRO has taken cold spray, which has been around for years, and they've developed their own proprietary process around it. They're doing some incredible things, which I'll show you some examples a little bit later. There's a company in South Dakota in the US that's doing cold spray called Flexible Robotic Environments, and then Trinity College in Ireland is also doing a version of cold spray. And what they're doing there is they're spraying material. They're spraying metal powder at high speed and building up parts from it with no heat at all. No heat at all. Just the velocity of the particles causes them to plastically deform and bond. And you build up these incredible parts just by hitting powder into other powder with no heat involved at all. It's pretty incredible. And it's similar in some respect to the Arbor freeformer because that's spraying out particles of powder as well. So I think what's important about all of this really is prior art. So to the extent that you run into any of this and you're looking at, well, what came first and what's patentable and what isn't, well, all of this is related to each other. It's worth to consider. Now, PolyJet is a different type of material jetting. It's not what we were talking about before. It's not aerosol jet. It's not direct write. Here you actually have multiple inkjet-like nozzles. And they're spraying material from different directions out of different nozzles. And they're building up a part using those multiple nozzles. And they're using mostly photopolymers, and then they're being UV cured as they're being built. And here the great thing is that you can make hybrid materials as you go along. I'll show you examples of that in a moment. Post-processing is to remove supports and to remove the excess powder, but you can make finished parts. And 3D Systems is one company that has a material jetting process. And you can spray different materials in different proportions and create hybrid materials on the fly. So you can have a part of a product that is rigid and part of a product that is flexible all in the same build. And so you're changing the characteristics of the material as you're spraying it, as you're jetting it, so that you have rigidity when you need it, flexibility when you need it. And same thing with this razor here. So you have flexible razor handle and rigid where it has to hold the blade and the buttons. So this is all one build to build this. And these machines are not nearly as expensive as metal machines. They go from about $60,000 to almost $250,000. And Stratasys is also in this space. They probably have the more sophisticated technology. Their Connex machine is kind of like a benchmark machine. And they talk about creating digital materials on the fly because they can print or jet 3 different materials at the same time and decide what their properties are as they go along. As I said before, they could be flexible or not, or they and changing colors as they go as well. And these machines run from about $20,000 to $600,000 depending on the size of the build chamber and also on whether it's multi-jet or single jet. And then Aerosol has just come out with a machine that is in this material jetting space, and they call theirs thermal metal spray. They're doing what cold spray is doing, except they're using heat, so they're just spraying. Material, metals or powder at 3 times the speed of sound, and they have a 5-axis CNC mill, and they do intermediate milling of the layers as they go along. And they're able to use this to create alloys as you're building, but they're spraying material and causing it to bond with the use of heat. Now that was material jetting. Now we get into powder bed fusion, and powder bed fusion is where most of the functional end-use metal parts are coming from. Although this can be done with plastics as well. And this is where you see the real alphabet soup of 3D printing. We have 3D Systems that calls their process direct metal printing, or DMP. We have EOS in Germany, which calls their system direct metal laser sintering, but other people use, even though that's their trade name, I don't think it's really protected, and it's kind of commonly used in the industry to refer to a metal powder bed process that involves a laser, even though it's kind of EOS's trade name. Then Renishaw in the United Kingdom has metal laser melting, or MLM, and then there are plastic and metal processes called selective laser melting or selective laser sintering at various companies in Germany and the US. And then there's a company in Germany called Laser Fusing, called Concept Laser, and their process, they call it laser fusing. But all of these trade names and all of these quasi-generic names and all of these acronyms, they all fall under the heading of powder bed fusion. And what powder bed fusion is, and there's some other companies that do this as well around the world. One in Germany, a couple in Germany, several in China. And these are the expensive machines, 1.6 or 160,000 to almost $2 million. And the way that these machines work is you have a bed of powder, and it can be a bed of metal powder or a bed of plastic polymer powder. And then you point a laser at it, and then you fuse the metal in the bed layer by layer by layer with that laser. So you're building up the product layer by layer by layer by pointing a laser at the bed of powder. And these parts have to be anchored to the base because otherwise they will warp, and it's all done in a vacuum. And in many cases, the surrounding powder actually provides support because it's in a bed of powder. So if something's being built up out of the powder, it's still got powder all around it because it's only applying the laser where it's really needed. So you don't have to worry so much about the overhangs or providing support material. They just are naturally supported by that powder that's underneath as it's being built up. And now this example here, this is the famous GE fuel nozzle, and a colleague of mine who's a consultant said that no presentation on 3D printing is complete without a photo of this fuel nozzle. This is, GE is making this fuel nozzle for the leading edge aircraft propulsion engine. There are 19 of them in each engine, and they were originally 20 parts. They're now, by 3D printing, they're reducing from 20 parts to 1 part. They're done in cobalt chrome by the powder bed fusion process using, I think, the EOS machine. So it's their direct metal laser sintering process. It can be done with all types of metal powders. And each one of these nozzles reduces weight by 25% compared to the way the nozzle used to be made. So you got 19 of them in an engine. You see, you're saving a lot of weight. And Alaska Airlines did a study where they removed five magazines from an airplane and saved $10,000 a year in fuel costs. So to reduce the weight of these 19 nozzles by 25% is quite potential fuel savings. Now, here we see the strength of lasers, 400 watts to about 1 kilowatt, different size build volumes. These parts have to be heat treated after they come out of the machines. But they can be used for finished structural parts. Parts that actually are structurally sound. They're as strong as wrought parts. And you can have very complex geometries. This is a acetabular hip cup. They're installed in about 50,000 people around the world that have had their hips replaced with these cups. They have a semi-porous surface structure so that human tissue can grow into the pores, and so it can become part of the human body. They're made out of titanium. This is a bridge strut, which was made by design through topological optimization, so that you only have material where you need it. And the parts that are made this way, or designed this way, and made this way, they really, I always say, they look like they were grown, not made. They look like they were grown. And this is one of the beauties of not only 3D printing, but also of combining that with topological optimization and using powder bed fusion processes, is that you can make parts that don't look like any part you've ever seen before. They just have the strength where they need it. They're a lot lighter. You've gotten rid of a lot of material, so they're fundamentally cheaper to make. Now, another company that does a similar type of thing is OurCam, which is in Sweden. And instead of using a laser, they use an electron beam. And they're doing exactly the same thing with powder bed fusion as with the laser beam, except they're doing it with an electron beam. And this photo is significant because this wasn't a situation where they made all of these acetabular cups and then stacked them up for this photo. They were built this way. They were built in the build chamber like this. So when people say you can't use 3D printing or it's not practical for mass production, that may be true. But for a situation where you need a part production, it's not a tiny amount of quantity, but it's not a huge amount either. It's kind of in the middle. You can really build as much in your build chamber as will fit. Now, electron beam melting, OurCam only supports titanium, but companies are experimenting with using their machine with other types of material, including CSIRO. I visited CSIRO the other day, and they have an OurCam machine. And even though OurCam only supports titanium, they support their customers working with other types of materials. And so customers are branching out, and they're using the machines with other types of materials. Now, these are faster than using electron beams, faster than using a laser, and you have less residual stress with electron beams than with a laser. But the parts that come out of these machines aren't quite as refined as if you use a laser. So there's kind of a trade-off there. But again, you can make structural parts with this, and this is like aircraft grade. materials, the parts you can get out of these machines are aircraft grade. There's another company called Matsura in Japan that makes a hybrid machine that combines the powder bed fusion process with a CNC mill, and they mill every 10 layers. The machine costs $1 million, but again, they make beautiful parts come out of these machines. Now that is all in powder bed fusion. The next to the last type of technology is sheet lamination, and here this is kind of like the freakiest type of technology. This is there's a company in Ireland called M4 Technologies, and what they do is they use regular photocopying paper in their machines, layer by layer by layer of photocopying paper, which is cut with a stylus, and you can have full color. This is a model, not the real head, but the model of one of their employees. It's another one of their employees, and what these are good for is models and prototypes. They are trying to get these in the schools. They've told schools that buy these that they will supply paper for 2 years, all the paper that you need for 2 years. The price of them is very reasonable, $36,000 to a little less than $50,000. They can be full color. I saw a spring that was made with this process. It was about this tall, and it was a coil spring, so it was a fairly loose coil, so it coiled about like that, its total height. And it was incredibly strong, incredibly strong. It had all the springiness that you'd expect a spring to have, and it was made basically of layered paper. Now, there are other companies that do sheet lamination. One of them is called Fabrasonic, and their process they call Ultrasonic Additive Manufacturing, or UAM. And what they do is they fuse layers of metal foil. And the great thing about this is you can embed sensors, or you can have a layer of some material that's a signal layer. So, for example, if it's something that wears, and you build the outer layers out of the material that's the strong material, as it wears, eventually it gets down to the wear layer that you can see, and now you know it has to be replaced or repaired. And one of the things they make with this is Arbor, which is pretty incredible. I met a CEO and saw some examples of what they do fairly recently, and they also have a very big machine, as you can see. So that's sheet lamination. The last type of process is that photopolymerization. And this is also called DLP, or digital light processing. It's also called stereolithography, or SLA. This is the original, very first type of 3D printing. Well, it wasn't called that at the time. It was invented by this guy named Chuck Hull in the 1980s. He called it stereolithography, or SLA. SLA is kind of a trade name of 3D systems, but it's commonly used to refer to this type of process, even though it's considered to be 3D systems process. There are other companies that make a type of digital light processing, Envision-Tech in Germany, DWS and Lithos, and then Formlabs and B9 are consumer grade vat photopolymerization companies. Their machines cost about $2,000. Autodesk, which is a big company, has come out with its own consumer grade machine that they actually call Ember. This is wrong. Originally when it first was announced, it sounded like they were calling it Spark. Actually, they call their software platform Spark, and they call the machine Ember. And also Lawrence Livermore is doing a small-scale version of this process. And as I mentioned, it was developed in the 1980s, and what you have here is you have a vat of photopolymer, and then you have a laser, and the laser shoots, or projects, I should say, projects the image of whatever it is that you're trying to build onto the surface of the photopolymer, and it's a UV, it's a photopolymer, so the laser is curing the layers of photopolymer layer by layer by layer and projecting the image on the surface. So the part seems to kind of grow out of the photopolymer. And you get very smooth surface parts that come out of this. Some of them are great for finished part use, some for prototypes, and it's great for jewelry molds. And they run in price from about $5,000 up to about $600,000. Now, that's the 7 basic types of 3D printing technology. Now, a lot of people view these as game-changing technologies, and they are. But there are some new processes that I call game changers among game changers. And one of them is voxel 8. And this is a startup, a woman named Jennifer Lewis at Harvard, who's very well known in this area. She's created this machine, the voxel 8, And this machine has the capability of printing the outside structure of a device and the circuitry in it. So now it's fairly primitive now, but she's printed a small drone, and so you have a plastic drone that was 3D printed, and then the circuitry for the drone was 3D printed as well, and it can fly. So this is the beginning of moving this technology from 1764 into the 21st century. So this has great potential. Then there's a company called Impossible Objects. And Impossible Objects has, in their alphabet soup contribution, they call their CBAM, CBAM, or Composite-Based Additive Manufacturing. And what they do is they take layers, sheets of carbon fiber or aramid fiber, Kevlar, or sheets of fiberglass, and then they lay down powder on top of that sheet, and then they spray the powder with a proprietary agent. We'll tell you what that is. Brush away the extra powder, and then they compress the layers. And they say that with this process, to get a finished product, and they say that with this process you can build functional parts in up to 10 times faster than with any of these other processes. And that the parts that come out of it are 2 to 10 times stronger than the parts that come out of any of these other processes. And the strength to weight ratio is great, because even though you get a very strong part with powder bed fusion, if you're using metal, with this you can get a much lighter part with the same strength, because you're using layers of aramid fiber or carbon fiber or fiberglass. So this is a startup. And they're just starting now to try to commercialize this process. I think it has great potential. They're a great acquisition target. They're a great licensing target. Then there's a company that just announced this process within the last, I should mention Impossible Objects. I was a juror for the International Additive Manufacturing Award, and this was one of the submissions, and I was just really blown away by it, and I think that we'll be hearing more from them as time goes on. There was a submission for the 2014 for the award that came out in early 2015. Now Carbon 3D, what they have is a process that's it's a vat photopolymerization process, and it's widely kind of hailed as a breakthrough, because supposedly the parts that come out of it are layerless, and it's much faster, and you get a very high quality product. I don't know whether this is really a breakthrough. I think that it is. It could be an incremental improvement on vat photopolymerization, but their contribution to the alphabet soup is CLIP, CLIP, Continuous Liquid Interface Production. And so right now in the industry, people talk about this as if it's a breakthrough. Finally, in the breakthrough category is HewlettPackard. And HewlettPackard's been saying for a while that they're going to come out with a 3D printer. And in fall of 2013, Meg Whitman said we want to own this space, and we're going to make an announcement in June of 2014 of our 3D printing technology. Super secret. People who work in the company said they've never seen anything so secret before. And just before June of last year, they announced that they're not going to make the announcement in June. They said we're going to delay our announcement until October. So on October 29th of 2014, they announced what they call multi-jet fusion. And multi-jet fusion uses 30,000 nozzles that spray up to 3 million droplets per second of material into a bed. Then and they have an X and a Y moving carriages. So the X carriage comes over and deposits material, and the Y carriage comes over and sprays what they call agents on it and gives it a shot of energy. And then the X carriage comes back and deposits more material. So they've combined material jetting, something like binder jetting, although they say they're not binders, and powder bed fusion. And because the system can be reconfigured and those processes can be done in different orders, it can also be directed energy deposition. So what they've done is instead of going down that single technological path road that everybody else is doing, what they're doing is they're combining these technological paths, and they're bringing to bear their decades of experience in the 2D printing space and technology. And they say that to make 1,000 gears as a sample takes 83 hours with material extrusion, and it takes 3 hours with multi-jet fusion. So much faster. They say the machines are going, they haven't given a price, but they say the machines are going to be very reasonably priced, very high quality parts that they'll be able to be full color. And they're beta testing them this year, and they'll start selling them at the end of next year. And they made this, this link, this chain link, using the process. And it's believed that this was nylon that they used in the process, and this car is hanging from this link. So very strong, but lightweight, build fast parts. So this is a game changer, and I think it's going to force all of the companies in the industry onto research and development paths that they wouldn't have gone on otherwise. It's going to be great for the industry because it's going to force additional innovation. They won't be able to be as complacent as they've been on their own technological paths where they've been cross-licensed and kind of this peaceful coexistence. I think it's really going to shake things up, and I think it'll be good for the industry. It may lead to more litigation. I hope not, because I think litigation would stifle the development of the technology and its adoption. Now, one other game changer, potential game changer, is high-speed sintering, again, HSS. This was developed at Sheffield University, it was developed at Loughborough University and moved to Sheffield University, but Loughborough is doing the licensing. And this process is said to, not a lot is known about it, but this process is said to rival the speed of injection molding. So again, a potential game changer among the game changers. Now, there are other companies that like to get into this space. Ricoh has announced that they will have a machine in 2016. They haven't said much about what it'll do. Canon says they'll have one in 5 years, and they have a prototype directed energy deposition machine now. And Epson made an announcement in I think it was late 2013, it might have been early 2014. They said, we want our machines to make anything within 5 years. And that was an incredible statement because they have no machine at all. Right? So, well, at least not in the market. So they're working on something, right? So they could have something really incredible soon. And I say others with question marks because, first of all, I know of some other companies that are working on machines that are confidential. But also, if you look at certain types of manufacturers around the world, especially Japanese consumer electronics manufacturers, they're running out of things to sell. A lot of things they used to sell, there's no market for them anymore because all we need is a smartphone and an iPad and maybe a TV. I wouldn't be surprised if we start to see consumer electronics companies venturing into this space, especially on the consumer level, because they are running out of things to sell. They're going to want to get into this space. And another company that might want to get into this space is this one, Apple. They haven't said anything publicly, but they have several patent applications pending for 3D printing processes, and they've been published. They're not. We don't represent Apple, so at least I don't think we do. But these are published applications, so it's out there. So what they're planning to do is really anybody's guess. And then this company, Samsung, in October of 2014, they announced that we won't be getting into 3D printing anytime soon. Probably not until at least 2025. We don't really see a value proposition there. That was in October of 2014. 4 months later, in February of this year, they formed a task force that the job of which is to figure out how to make 3D printing work for them. So I think they might have sensed in October, when they made that statement, that maybe they were making kind of a Kodak type decision, you know, and they revisited that decision, and now they're looking at getting into this space. Now let's talk about what's happening here in Australia. This is where we're going to end. Now there's a lot of exciting things happening here, and I was talking to Mike earlier. Mike, where'd he go? There he is, right there in front of him. We were talking about getting, no, actually I was talking to you about something else. We were talking about getting them into the schools. And Maker's Empire and the 3D printer are companies here in Australia that have dedicated themselves to getting 3D printers into schools. So, you know, if your kids are in a school, you think they'd like to have a 3D printer, and they should, you could contact these companies and see where you're on the list or what you can do to help move that along and get a 3D printer into your school. On the university level, University of Wollongong and Queensland University of Technology have the first master's degree in bioprinting in the world. And I haven't talked at all about bioprinting today, but it's a big industry in and of itself. And so the first master's degree in bioprinting you can get right here in Australia. Then RMIT University, I mentioned earlier that they used Optimex lens machines to repair those turbine blades. They also have a high-speed nanoscale 3D printer, and these nanoscale printers can print on the scale of about 1/10 of the thickness of a human hair. And then there's a company in Melbourne called Objective 3D that is what we call a service bureau. They have a lot of machines, and they can make parts for whoever needs the parts. So they're mini factories. They have a $7 million factory they just opened in Melbourne. The Australian Army is using 3D printers to make their own drones, and they're also looking at other military applications. But there's also a dark side to 3D printing, and some of it has come to roost here in Australia. Australia was the first country in the world to introduce legislation to ban making 3D printed guns, at least out of plastic, because when Cody Wilson made his 3D printed gun in the United States in 2013, it got a lot of press. A lot of people were worried about people 3D printing guns. It's a lot easier to get guns in other ways than to 3D print them. But Australia introduced legislation to make it illegal to 3D print at least a non-detectable gun, and to possess or share the digital blueprints for doing so. But I think this legislation was defeated. Now in New South Wales, we had some enterprising criminals, probably descendants of some of the originals, who were 3D printing fake facades for ATM machines, for money machines, that had skimmers inside, so they could skim your credit card when you put it into the fake facade. And originally they had to come back and they had to download data, but now they can actually get it through Bluetooth from the car. They just have to drive by and they can get the scanned information. So there's probably some of these actually still installed around, this is in New South Wales, that people just don't realize they're there. And then right here in Queensland, police in a raid seized these 3D printed gun parts. Hadn't been assembled, but along with drugs and real weapons and other criminal stuff. That was right here in Queensland. Now, this though is what I call the bright side of 3D printing, and this is a 3D printed jet engine that was done at CSIRO, Monash University, and Deakin University with machines, with the OurCam machine that's at CSIRO and the concept laser machine that's at either Monash or Deakin, I'm not sure which. And this is the first fully 3D printed jet engine in the world. World-class work being done there at those three institutions. And this was done with a combination of cold spray and powder bed fusion. So these are fully dense metal parts. And then only within the last couple of weeks, this was announced. This is the Rutherford jet engine that was done in New Zealand by Rocket Lab Ltd. And this is done in, it's either cobalt chrome or, no, it's in titanium. Beautiful piece of work. And that's done again with powder bed fusion. Now finally, we have this cool bicycle. And this cool bicycle, that cool bicycle right there, that's my bicycle. And this bicycle was made by a company in Perth called Flying Machine. I heard about Flying Machine around sometime in maybe February or March of last year, and I was scheduled to come here to speak in Melbourne in July of last year at the Inside 3D Printing Conference and Trade Show. And I thought it would be really cool to ride a 3D printed bicycle into the room where I was giving my speech. So I commissioned this bicycle, and what they do is they make custom bicycles. That's what they do. So they have a website. You measure yourself in every way, in ways that you never thought you'd be measuring yourself, and before you have your wife do it, she never thought you'd be measuring it that way either. And then you send them the information, and you pick out the colors and everything else. And parts of this bicycle, and I'm going to tell you the truth, parts of this bicycle, all the connecting lugs, these were all 3D printed. The tubing was not, but it can be now. And it probably could have been at the time. But my bicycle, I have to be honest about it, only the connecting parts were 3D printed. And it was done at CSIRO. 3D printing was done at CSIRO. Now this is me at CSIRO on Thursday morning. I went to visit. This is Stefan Belizia and in the cold spray lab. And what I'm holding in my hand is a titanium pipe. And this titanium pipe was made with cold spray. It can be made in any diameter and any length with no heat from titanium powder. And everything on this table here was also made with the cold spray process. Really, really incredible process. And this is me standing next to the OurCam electron beam machine where all of these connecting pieces were made. And I'm holding in my hand a sample of one of the connecting pieces that was made in that OurCam machine. And then, unfortunately, my bicycle wasn't ready by the day that I had to ride it in to give my speech. So CSIRO had a booth at the trade show, and Flying Machine had some of its bicycles in the booth. This is one of the bicycles that they had in the booth. So again, all of these connecting pieces were 3D printed by CSIRO. And I rode this bicycle in to give the speech. And this is Matt Andrew. He's the guy who owns the Flying Machine Company in Perth. And I've given you the website there in case you might want to buy one. Right? They could use the business. And I think it's great. You know, they're making bicycles in Australia and they're doing it 3D printing. So that's 3D printing technology, and that is what's happening in Australia. And as you can see, this can be very disruptive. I embrace disruptiveness here, and I can't wait to see where it heads next. So thank you very much for your time, for having me. Follow my tweets. This is my staff. Thanks.
We've gone for a while, but has anybody got any questions for John? We've obviously got a very disruptive technology that I think is going to affect any industry. You actually put your mind into the application. We've got researchers at UQ looking at, who recently bought a 3D printer looking at food applications. Anybody else? Anybody have any questions?
Yes, sir.
A lot of the manufacturing processes around things like aeronautical manufacturing, aerospace, are really confined to an enormous amount or enormous number of regulatory testing standards and so forth. How do you think that something which is a novel, disruptive method is going to work into what are some very legal, technical sort of industries like that?
Well, there's a lot to that question, really. One area, this is one of the reasons why I say the technology is in 1765, because the results that you get from one machine to the next printing the same part, they may not be entirely consistent. There's a lot of room for standards development. There's a lot of room for material control and machine control and process control. So right now that has a ways to go. And there are some companies like Concept Laser that have this continuous monitoring of the process as it goes along. They can tell if something goes wrong. If they might be building 50 pieces on a bed, and they can tell if something goes wrong with one of them, and they don't have to stop the process. They can just keep building. So there's developments being made in that area to try to get consistency and to get a high quality. But yeah, these things are still going to have to be qualified by whatever business, whatever industry it happens to be. If it's an airplane part, in the U.S., the FAA is going to have to approve it. That's a long, involved process. It takes a while. But we're not talking about something that's going to end here. We're talking about our whole future here. So in time, I think we'll have greater and greater adoption of this technology, and we'll have better processes, and we will have more and more qualification as we go along. But the other part of your question is I mentioned at the beginning that this cuts across all types of technology and all types of IP. It cuts across all types of law as well, all types of regulation. I was giving a speech in Washington in February, and someone asked, it was to law students, and they said, well, if we're looking at what area to go into in law, I said, what legal industries might we consider? And I said, all of them, because there's product liability issues here, obviously. There are taxation issues, because if you can make things away from control, like I was talking about earlier, without anyone knowing you're making it, does it get taxed? Those are turbine blades that those companies are making. Used to sell the turbine blades, pay tax on that. Well, if the company's making their own turbine blades, is anybody paying tax on that? If you do that on a large enough scale, how does that affect taxation? So there's a lot of legal issues across, and insurance is another one, export control of technology. There are a lot of legal issues across virtually every field. If you're talking about food approval, and bioprinting has FAA and US FDA considerations. So virtually every industry, every type of law, every type of technology, they're all involved. Anybody else? Yes, sir.
Yeah, John, we haven't quite touched on the patent side of things as patent attorneys, and not talking about the technology and the patents associated with the actual technology, but you know, products being manufactured, as you said, anywhere in the world by anybody in their home, and you know, the infringement issues that go with that. I mean, where have you seen that question or those questions being asked, and how's that being developed?
Well, that's a lot of what I talk about in some of my other presentations. I didn't want to duplicate the same thing I did in Melbourne here, but right now there is very little patent litigation in this space. And what is there isn't really even interesting to talk about. But the potential is that, and what I talk about is this concept of 3D printing things away from control, where you can make things without anyone knowing about it, without anyone being able to control it. As that proliferates, sure, you can patent whatever that is, but does the patent mean anything? I think ultimately, as 3D printing away from control increases, any intellectual property covering those things that can be made away from control, the IP becomes irrelevant. It might exist, but it becomes irrelevant. So I think it can have profound implications, and in addition to that, there's this issue of customization. 3D printing lends itself to customization, so rather than making a million of one thing, you can make a million things that are all different. Well, can you write patent claims for that? Well, you may not be able to. But I say, well, it doesn't really matter because the customization itself becomes the protection. If you're making highly customized products, they're customized. So what do you need protection for? What you need to protect is the infrastructure that allows for the customization. So it might be the underlying software or the underlying processes or what I call the secret sauce, the trade secrets that go into that. So you protect all of that. But if you're dealing with highly customized products, well, you may not be able to write patent claims that would cover that. Still, you'll be able to patent write claims to cover processes and machines that do these things, sure. But that's all what I call within control. But anything within control, IP system continues to work as always. For anything away from control, it can get really stressed. But we're not there yet. I think we are getting there. And an example of that is that everything, I was talking about this with somebody earlier, everybody in the industry who wants to go out there and talk about what they're doing, what they're making, they're under NDAs, and they say, we can't show you most of the things we're making. We have an NDA. We can't show most of the things that are being made with this technology. And there's a lot of reasons why that might be true, but my suspicion for one of the reasons is that a lot of it is stuff that's being done away from control. A company is saying, I'm going to make my own. I'm going to have it made by this service bureau. I'm going to sign an NDA. Nobody's going to know what I'm making. So what, is that infringing? A lot of stuff isn't covered by any IP at all, but those things that they're making at that service bureau under that NDA, a lot of it may be infringing, but there's no way of knowing. That's away from control, and that will disrupt the system without you even realizing it's happening. Anybody else? No? Okay, well, thanks very much.
Thank you, John. John made a very good point. Well, one, I can commend John's Twitter handle. Follow John. He's got a lot of really interesting articles, ones he writes himself as well as general observation. I can also recommend following the LESA ANZ Inc. Twitter handle. We tweeted all the way through the conference, and we had some really good reception to that, including on John's topic, and actually that was picked up by one of the 3D printing organisations, which was really useful. Made a good point. You missed a great talk in the LES ANZ conference in Melbourne last week. I can recommend everybody to keep an eye out for next year's conference as well. Hopefully we'll see you again soon. John's a regular visitor. It's always great to see you.
Thank you.
So, thank you for coming.
Thanks for having us. Yeah, thank you.